Good morning, everyone, and thank you for inviting me to your place. And I hope you're having a cup of tea or something so that you can enjoy some refreshments while we're going. Now, you all know, of course, that the topic today really is to do with insights and what is really causing weather change. And we'll deal with the difference between weather and climate a little later. But let's give a quick overview. All the energy that we experience in this world comes from the sun, it's solar energy, and the corona or gas around the sun operates a little over 5,000 degrees, and it sends out radiation. Now, so that we're all on the same page, electromagnetic radiation, what we experience predominantly is light energy. So electromagnetic energy is more than light energy. It's ultraviolet and so on. We'll talk about that. But that's what's coming through space. Now, it hurtles through outer space coming from the sun, and outer space is absolute zero, almost absolute zero, minus 273 C. So that's almost absolute zero. And the pressure is virtually a vacuum. So there's nothing out there. Now, as a consequence, and this is why it's important, there is no heating at all. That energy has nothing to do in outer space. It's there, it's powerful, but it has nothing to do because it's not thermal energy at that stage. Then it comes down to the outer Earth. There's the thermosphere, the mesosphere, there's in the stratosphere. Now, the stratosphere is the layer above where most of our areas. We'll talk about that in a moment. But 15 to 50 kilometers up, we have the ultraviolet energy coming from the sun, that electromagnetic energy part. It makes oxygen, turns oxygen, not a large amount of oxygen there, but it turns into ozone. Now, it's important to see that 6 months of the year in the South Pole and 6 months of the year in the North Pole, it's dark. So that's why we get an ozone depletion. There's no ozone hole per se, but there's an ozone depletion North and South Pole every year, except we have put some chemicals up there that use up some of the ultraviolet, and this ultraviolet, of course, can't be used, and so it depletes even more. But that's another issue. So fortunately, this UV, this is the high energy UV, is used up. If it didn't, it would probably kill us. So most of it's used up there. Now, the rest of the energy comes into our troposphere. Now, that's where we live in the first 10 to 12 to 17 kilometers, depending what part of the Earth you're on. And that troposphere contains about 80% of our air mass. And of course, the air mass is mostly nitrogen, oxygen, and argon. In fact, it's 98.8%, 98.8%, which is almost 99% nitrogen, oxygen, and argon. And it's interesting to note that these three gases have no effect on radiation. Now, if the press will give you the honest treatment, radiation from the sun has nothing to do in outer space and nothing to do on Earth when it gets into the troposphere with oxygen, nitrogen, and argon. Now, some of the UV, not all of it, is used to make ozone the next level up in the stratosphere. Okay, so what we've got is then nitrogen, oxygen, and argon, and then the radiation, the rest of the radiation comes down, and what's the next one? Well, it's water vapor. And water vapor in New Zealand is about 1%. In the tropics, it's about 4%. And it's, say, 1% on average here. So the top four gases now, water hops in and takes up number 3 position because it's slightly higher than argon. So nitrogen and oxygen are dominant, then water vapor, and then argon. Now, argon is simply an atom. It doesn't react. Like helium doesn't react with anything. Argon doesn't react with anything, and so on. Neon doesn't react. They're the rare atomic, just atoms only. They don't have not a compound. So when you add water in, you get 99.8% of the atmosphere. 99.8%. Now, if we separate out, I've got that in yellow there, you'll see that water vapor is the only greenhouse gas in the top 4. Now, what do we mean by greenhouse gas? Well, there's no greenhouse in the world. It's a stupid idea. There's no roof, no walls, and the warm air doesn't rise, hit the glass or whatever and come back down again. So, but let's just for the argument, keep the concept clean. greenhouse gas is one that absorbs electromagnetic energy. That's what a greenhouse gas is. So if we separate them out, the greenhouse gases are less than 1.1% of the whole atmosphere. Water vapor is number 1. Carbon dioxide is number 2, and methane is number 3. And water vapor is about 25 times higher than carbon dioxide. And methane is quite small. So what's next? So what's next, of course, when the energy comes from the sun up here, from radiation comes in, the very big next thing is clouds. Now the clouds reflect, scatter, absorb and transmit. Reflect some of the energy coming in, like the visible light, and you know that on a cloudy day, scatters it, absorbs some of it and transmits it. So these are the greenhouse gases, basically those 3, they're the top ones. And by the way, water vapor is about 5,000 times higher than methane. So it's not a very important gas after all, even though the press says so. Okay, so we come to clouds. So what do the clouds do? Well, there's 66% coverage of land and sea in the world. So the biggest coverage of a body, if we like to call it a body, would be clouds. The next one, of course, is oceans. The oceans are 71% of the world. So 2/3 of the world is ocean, 2/3 of the world is clouds, approximately. And so the key issue, because clouds are little liquid droplets and very fine, they're not big because they don't, otherwise they'd rain down on us. So they stick up there in little micro droplets. And the big or the dominant thing in the atmosphere and on the earth is water, liquid water in droplets and so on. Now, I could spend a whole, and sometimes I've done this, just spend a whole talk on this. There are 4 vital things that are not covered today in the press or in the governments and so on. The biggest thing in the world today is evaporation, the biggest activity. And you say, well, hang on, we don't hear much about evaporation. Well, do you know how much water evaporates every year? Well, I'll tell you. It's 423 trillion tons a year evaporate. Now, what does that mean? It means 423 million tons. 423 million tons evaporate every year, and 423 million tons rain down, either snow, hail, sleet, or rain every year on both oceans and so on. Now, this topic, humidification, what happens then? As you know, on a hot day and you've been working in the garden, you get sweaty, and if you don't put something on, you feel cold because the water is evaporating from your skin. You feel cold because it needs energy to evaporate, and it humidifies the air. If you go to the tropics, you're sweaty because there's high humidity. If you go to out in the bush outside of Australia or in parts of New Zealand, you feel quite dry because there's not a high humidity. Now, this is a big topic, but I can't deal with it today. But I've written got a chapter in a book coming out on mainly on that stuff. Now, once it gets up there, it starts condensing, and it condenses to form clouds. Different types of clouds. Some of the clouds absorb energy, some reflect it, and so on, transmit it, as we said, and then it precipitates. Well, 423 trillion tons, million tons precipitate as rain, hail, snow, or sleet, or drizzle every year. So water is a big factor, but we're not going to just spend our time on that, although I could. But let me just say this, even if you get nothing else out of this morning, the more the earth heats up for any reason, the more water evaporates. The more water evaporates, the more clouds, and the more clouds, the more precipitation or rain and so on, the more cooling of the air, then the cooling of the land, and then the cooling of the sea, because most of it's, as we said, is 71% is the ocean. Next time you go in the car and it's about 22 degrees, you're driving along, and it starts to rain, look at the temperature. Within a few minutes, it's dropped 3 or 4 or 5 degrees. You can see that water, as rain, really cools. So it's self-compensating, self-adjusting, self-correcting, self-buffering. Powerful thing. Okay, so why don't we all believe that? Well, there's a reason. There's more than one reason. And the worst thing is in Wikipedia. If you go to Wikipedia, you'll find The reason why everyone's in the cactus. The kids are in the cactus at school. Well, the textbooks have still got it here. Miles will remember if he looks at his textbooks at the front on this subject, they left water vapor out. Nitrogen, oxygen, argon, carbon dioxide. These are the gases in the atmosphere. Wikipedia does not include water vapor. So therefore, it's taught in schools now. Therefore, it is totally wrong. So water vapor is always in the atmosphere. In fact, at the South Pole, the water vapor is a high concentration of carbon dioxide. So that's wrong. Now, to prove that this is not just a blind thing, if you go to Google, you'll find that they have diagrams, and each of the diagrams gives the proportion of the gases in the air. For example, there's nitrogen and there's oxygen, and these are the trace gases. Only one of them, that one there, mentions water vapor, 1 in 25. The rest of them don't even include. You go on Google and look at them up. Water vapor is not included. So that's wrong too. So who's getting the wrong picture? Mr. and Mrs. Average, the public. And it's totally wrong, and it gives the wrong impression. Okay, well, just moving on. Only 56% of all the radiation from the sun ever gets to Earth, because we've got ultraviolet, we've got infrared and visible. We just need to talk a little bit about that. Now, if we take white light, you're well aware that our eyes will pick up light, and we have a rainbow, or a school experiment, you had the red, orange, yellow, green, blue, indigo, and violet. Now, on the lower energy end, red, we have the infrared, which is this one here, infrared. It's about almost 50%. And on the other side is violet, which is the ultraviolet, now 8%. Now, your eyes pick up visible light. Your skin has little nerve endings. There are infrared eyes. They pick up infrared. So they're the eyes that pick up the infrared. And we feel warm when we go outside. The ultraviolet is the stuff when we become a geriatric like me, you get little spots and little damage to your skin, because and that's why people wear sunglasses, because ultraviolet damages. It's not the strongest ultraviolet, fortunately, but it's still important. Now these come to the Earth. That's electromagnetic radiation, infrared, visible, and ultraviolet. And they hurtle to Earth. We said there's 2/3 clouds and 2/3 ocean. So what's dominant when it comes to ultraviolet, blah, blah, blah? It is water in the oceans, rivers and lakes, and then clouds, water in droplets, and then, of course, water vapor. And water vapor, of course, is a gas. Okay, so when you boil a jug, you don't see water vapor, you see it condensed, they're little droplets. You see liquid water, but water is a gas. Now, just to give us a picture of how much energy is here, the solar energy arriving on Earth each day in one day equals all the energy used in Earth in 1 year on our planet. So if we take everything every factory, every car, truck, ship, plane, everything, all the energy that we use in 1 day, in 1 year, comes to our Earth in 1 day. That's just to give you an idea of the magnitude of energy that hits the Earth. Now, we've seen then that radiation is very important, but this is where the press and someone and the TV miss the point. So we're going to pause just on, we'll come back to it, but we're going to highlight that the Earth, there are lots of other factors, and the Earth is rotating. In fact, you're moving now at 400, and we are, including me, 460 meters a second. The Earth is traveling at 1,660 kilometers an hour around rotating. And of course, we have a tilt. If we didn't have tilt, we wouldn't have the seasons and the Earth coming in and giving summer in the north and summer in the south, etc. And then we have the Earth's revolution. It's not an accurate circle, it's elliptical. So we then have shifting further away and coming back towards the sun. We have clouds. We have storms and typhoons, tornadoes. All these things are over and above radiation, and often they're just left out. Hurricanes, they're massive movements of in the air. And of course, we have then discharges of lightning. Lightning is hotter than the sun, not very big, but it's much hotter than the sun. And then, of course, we set up macro motion on the ocean. So we then have movement of the seas. And of course, we've got other things like dust storms. We've got sunspots. Now, sunspots are tied up with the magnetic field and the flux coming from the sun, the magnetic field of the sun and the earth. If we didn't have a magnetic field, we'd die, and we won't go into that today, but that's a topic in itself. And last year, 70% of last year had no sunspots whatsoever. That means a period of darkness up in those spots, which is inactivity. And so this year we've had several months with no sunspots. Then we have solar flares, and so particles from the sun hurtle towards Earth, and these particles, called solar wind, two of them are going through our bodies every second. They're nuclei of either electrons or protons, or nuclei of helium atoms, and they're traveling at 700 to 800 to 900 meters a second. And it's called solar wind. Okay, so then we have on Earth, we also have the Earth, because it rotates, we have a jet stream. The top part is a stable polar vortex, become unstable, and so the ice floating on the North Pole, the Arctic, shifts in terms of thickness. It's all floating, the whole lot's floating, but sometimes it's 1.8 meters, sometimes it's 4 meters, 3 meters, and so that's caused by the shift of the wind around there. If you see this movement, you see that sometimes the jet stream takes hot air from the, let's say, the Sahara up to London and up to Europe. And they say, look, it's weather change, it's climate change. No, it's not. It's just the movement of warm air caused by the rotation of the Earth, not radiation. Now, of course, we've got all the massive air currents. That's worth a talk in itself. But to add to that, which we need to talk about today, is just to say there's a lot of ocean currents as well. Ocean conveyor belts have massive movements. And the latest problem in White Island was due to an eruption not too far away, and then the movement of water came across as well, hot water in that area. So these are all factors over and above radiation, but there's more. If we just take the difference between mountains and valleys and inland and so on, we have coastal and so on zones and inland zones, we get differences in weather. The Earth's tilt is important, and that's shifting, by the way. I went to, where was it? Up in Norway, I think it was, or in Sweden. And it shifted in 40 or 50 years, it shifted 200 meters, the actual tropic of, is it Capricorn? Cancer. Anyway, the level up there, 66 degrees north. Anyway, the Earth's rotation in a day, it's not exactly it's changing a little bit. We've got the Earth's precession because it's tilted, and so the axis is precessing. Earth's elliptical orbit, it's not a circular orbit. You've got the magnetic field variations. You've got the lunar cycle effects, and we won't go into that, but the Earth will wobble if we didn't have the moon. And tectonic plates. Now, 80% of all active volcanoes are under the ocean. And these are hydrothermal vents and fissures. You've got one near the southern tip of South America, and it's taking the ice from a shelf underneath. And people are saying, caused by climate change. Rubbish. It's caused by a hydrothermal vent. And so there's some melting ice sheets melting from underneath. Now, as the Earth rotates, heat travels from a high temperature to a low temperature, so there's energy always traveling north and south, hot equator to the cold poles, and that's then added to the circular motion. So what have we got? We have got people, all they're worried about is radiation and fossil fuels. That's all they're worried about. Well, fossil fuels. Okay, so we've got a myopic view of the whole thing. But we need to come back to radiation just to make sure we're all on the same page here. So we'll deal with that. Now this will open your eyeballs, because I've done this so that you can see what's really happening. Now this is energy from the sun arriving on Earth, arriving on the troposphere. The wavelength is about 0.2, and that's on the ultraviolet end, through to about what we call 3 micrometers. Now, when we say wavelength, if you've got a wave and you go from top to top, that's a wavelength, the length of the wave, just like a sea wave. The peak to peak is the wavelength. So here we're 3 millionths of a meter. And let's have a look. This gives us the amount absorbed. The top will give us the 100%, the bottom is 0%. Let's look at carbon dioxide. Now, carbon dioxide, it's got one band, at 100 and one at about 70% absorbed. Ah, very good. Let's have a look at methane. Nothing, virtually nothing. It's about 10% and a very one spot. It only picks up infrared energy at a very thin spot. Let's look at nitrous oxide. Oh, very small, nitrous oxide. So the incoming solar energy. Now let's look at water vapor. Bang. Water vapor already outdoes one band of carbon dioxide completely, and also carbon dioxide has a little peak there, but look at 3 big bands of 100% absorption with water vapor. Now this is mainly in the infrared end. Visible light's down about here, and of course down further down here is ultraviolet. And so what happens is water vapor is clearly dominant. That's the gas. Water vapor is clearly dominant. Now, that's from the sun. Everything radiates. If you've got a hot cup of coffee, you can feel the warmth above it, but you can also feel the heat coming from it. The walls, if a wall is warmer than your body, then the heat will radiate from the wall. If your body's warmer than the environment, it's radiating out. Everything's radiating all the time. So the Earth re-radiates, but this time the wavelength is much, much bigger. It's 3 to 70. Remember the other one was 0.2 to 3. Now this is 3 to 70 micrometers, which is a millionth of a meter, these peaks, right? And so what we've got? Well, we've got 0 to 100%, as we've mentioned. It's coming up from the Earth, and we want to find how much is absorbed. Now, this is on the web. You don't need to be a rocket scientist or engineer to work it out. So if you look on the web, you'll find this, but I've done it so you can see it dominate. Now, look at carbon dioxide. It's like beauty. Look at 2 powerful bands, just 2 powerful bands, carbon dioxide, and both 100%. There's a couple little ones, but now let's look at methane. Methane's much better now with energy coming from the Earth. Nitrous oxide, it's much better. It's competing with some of the others because they're overlapping. Now, let's look at water vapor. Now, this is the shocker of today. Bang. Water vapor dominates. From 20 right through to 70, it totally dominates. I'll go back and show you. Let me go back first of all. See that? 20 to 70, nothing. The others do nothing. As soon as we put water vapor, water hits it, bang, knocks it completely. And so really water vapor dominates. This part in the middle here, which I'll just put the arrow on, this energy just from here goes straight to outer space. And that goes. The rest of the energy comes up and is not all absorbed, but it's absorbed by the other liquids. They're the greenhouse gases. So again, water vapor, the gas, totally dominates. Well, the question is, so what? Well, radiation, what's major? Water vapor. It's 25 times higher in concentration, as well as a better absorber of radiation, as we've just seen, but it's 500 times higher than in concentration in man-made carbon dioxide. So man-made carbon dioxide is only 5% of the carbon dioxide in the air. Small. And it absorbs, water vapor absorbs and then re-radiates. It doesn't store. People talk about blankets. You'll see it on the air and so on, blankets. A blanket gets hotter with you, and there's no such thing at all. And therefore, it's far better. So there's, as we've tried to show, there's far more than just radiation. Behind the scenes, what's the real meaning of reducing carbon dioxide? It's dollars. It's taxing. It's a means of hitting the Earth, scaring the hell out of people. So it's meaning for control, manipulation, and power. It's because radiation, carbon dioxide only does with radiation. It doesn't evaporate, doesn't condense, doesn't form anything else. Only water does that. So what is the big attack? Burning fossil fuels. Wow. Okay, we've got cars as one, but all the ruminating animals in the world put out more carbon dioxide than all the cars, buses, trucks, and so on in the world. Power stations, we've got to go gas, and the gas still, carbon dioxide comes out. Coal are anti because of particles, pollution, that's what they're anti, really. Go for renewables, don't you feel better? Well, solar's not too good. You've got to be in the tropics or semi-tropics, and then you've got to have a massive surface area. And if something goes wrong with the panels, you've got big pollution with the coatings of the glass. You've got wind turbines. Now, we'll show you a picture of wind turbines shortly. They're really a total failure. It takes 9 years before they have payback time. All the concrete, steel, and you've got to use coal-fired things to make the steel. You've got these special molybdenum in the big magnets. You've got the blades that are made out of a composite, which is you can't use. You've got to bury it. And so we've got hydrogen people saying, oh, hydrogen. Well, you've done an experiment, put a couple of drops of acid in water, put in a couple of electrodes, you get hydrogen, oxygen, but you've got to use electricity to make it. And also, once you make it, you've got to compress it. And once you compress it, it could explode because it's, the first, remember the chemistry thing, hydrogen, helium, lithium, beryllium, boron, carbon. Well, hydrogen's number one. It's this very small and it expands, it blow the sky high. So if a car had an accident with a hydrogen, forget it, you'll blow half the neighborhood up. Okay, what are the real problems? What are the real problems? Well, it's not fossil fuels and it's not carbon dioxide because that only affects radiation. And it's not just radiation because 99% of all the gases nothing to do, well, 98.8%, nothing to do with radiation. So what are the real problems? Well, there are two really major ones. Atmospheric pollution, and mainly that's particulate, but there's also toxic gases that they pump into the air and companies leave in the air. And the other one is incomplete combustion. And the incomplete combustion is the problem. When we had the old diesels, our lungs could get rid of the particles. In India, they burn cow pats, a lot of in other stuff, and China and so on, they belch out particles. There's many particles, but they do have other things like sulfur dioxide and phosphorus-based compound. But the biggest problem today is the diesels. They should not have been allowed. The particles are so small now when they are incomplete combustion, they get stuck in the lungs and the lungs can't remove it. So it really is a problem. So those two things are the major issues. And of course, then the finance, control, world, taxing, scare the hell out of people, make them depend on the government. It's socialism in disguise, really. Okay, now I just want to finish with a couple of examples here. This was taken from our place. It was at lunchtime back in November, rapid fog formation. There were virtually no wind. Just suddenly, this happened, bang. I thought, oh God, I'm sitting there having lunch. And I got my wife to testify as well. I took some pictures and it went still there, way out. It just slowly moved away. And it all happened with these in 15 minutes. And it was, I worked it out, there's 23 degrees. I got the temperature, indoor temperature, 100% relative humidity, and I worked it out as 20,000 tons of water per cubic kilometre, 1 kilometre high, 1 kilometre, 20,000 tons of water. That's fine mist. It doesn't precipitate, so it can't be denser than air. It's a fog. And it was the 7th of November last year, 1:30. Amazing. Now, again, this is another thing. This will blow your brains out because you can go to the humidity table yourself and pick any temperature you like. So you don't need me at all, but I want to highlight this. A 0.5 degree temperature increase. Now, we've had a 0.5 degree in our room at the moment, but outside produces more water vapor than the total increase in carbon dioxide over 100 years. I'll repeat that. A 0.5 degree temperature rise outside, if there's water, liquid water around, like a lake or other around, it produces more water vapor, the gas, than 100 years worth. Now, we go up 0.5 degree, we put in a half an hour. But we'd go to work, or what if we did go to work, 5 degrees, 10 degrees change during the day is quite normal. Now, here's an example. Here's the proof. I'm keeping the relative humidity constant, but if you go from 10 to 10.5, it puts up 118 parts a million. If you go from 18 to 18.5, it's 2 times the amount of carbon dioxide in 100 years. If you go from 25 to 25.5, and you can go on the thing yourself, that's 3 times. So this is quite massive, really. Changing the subject then, Auckland, sea level. There's no kick up in it. It's 1.29 millimeters a year. I think I said 1.65 before, but I mixed up with Sydney there. 0.65. Now 1.2 is 1/2 inch in 10 years. 0.65 is 1/4 inch in 10 years in Sydney Harbour. So you can see now these data go back from 1900, 1880, right through to about, not quite 2020 there, but it's amazing. So these facts are fully available on the web. Here's another, just a dramatic event. World War II, they had lost some aircraft two B-17 bombers in Greenland went down and 6 P-38s ran out of gas in a storm. There was one of them there. It's now covered by 91 metres of ice. Yeah, we've got problems, eh? 91 metres of ice, which is quite opposite. In 70 years, 91. Well, that's a metre a year extra ice above those, almost. Here's an example, just in America, 14,000 windmills, wind turbines have failed. And these are just the pictures, apart from the birds that get killed, which is a thing, a subject of its own. You've got fires and so on, collapsed things as well. But look at this. There's 8,000 blades chopped in half or quarters and buried. They've got to bury them because they can't reinforced fibre. They can't do anything else. Can't burn them. They can't do anything with it, but just bury it. And that's in America. And there's a reference here if you're interested. I can give you that. Now, just briefly, electric cars, great, terrific. Electric motors are better than the others, but if you have a traffic jam, you're going to, in the snow, you're going to freeze to death because the batteries won't keep you warm for 3 hours. You've got roads blocked, and if you run out of fuel, you can't start your car, and you block the rest of the traffic. And then what about summer? There's no, of course, aircon. These are just dramatic things to show about. We've got to be careful we don't just jump headlong. Well, we mustn't forget the following. Apart from radiation, there's breezes, thermals, winds, clouds, storms, hurricanes, cyclones, tornadoes, typhoons, jet streams. We haven't talked about jet streams, trade winds in the southern hemisphere. The roaring 40s you've heard about. There's ocean mixing, the tides, conveyor belts, waves, upwellings, thermal storage of the El Niños we haven't even talked about, La Nina. There are others too. Tectonic plate shifts, fissures or cracks, volcanoes, sunspots, with solar wind. We haven't really got into the Milankovitch cycle, the elliptical orbit and the lunar cycle. All these facts and more affecting us in our weather. Okay, so what can we say? Oops, I forgot. No, I haven't. Water vapor is the only gas that changes phase. That is, it's the only gas that goes changes state from liquid to gas to solid. Ice crystals up in the high clouds, snow crystals, snow particles up there. Change of phase. Now, all other gases, carbon dioxide, all other gases do not condense, do not change to a liquid in the atmosphere. This makes the atmosphere unique, and this makes infrared energy absorption quite different. So that's the bigger picture. And I would say that I hope that you gained a little bit of the bigger picture than just plain radiation. Thanks very much.
I'd just like to say thank you, Jeff, for your time, for your great presentation, and I think we should all express our gratitude.